Okay, so last lesson for acid-base equilibrium. We are going to talk a bit about indicators. So you know indicators change colors depending on the pH of the solution. But what you probably never realized was that indicators are actually all weak acids. So if you go to your data table and you go to the acid table, you're going to notice that there's this Ka column that we pretty much never really looked at before. Okay, this Ka column is here because all of these are actually weak acids, right? So if you look where it says suggested abbreviations, for methyl violet it says HMV and MV minus. These guys here are conjugate pairs, where this is the acid and this is the base. And you'll find that as you go through the whole table, that all stays true, right? The further we go down the table, you should notice that the Ka values get smaller and smaller the further we go down the table. That corresponds to the change in number of the pH, okay? So the higher or the bigger our Ka is, the lower pH value at which it's going to change colors. And then as we go all the way down here to the bottom where we have the trinitrobenzene, it's got a K of 1 times 10 to the negative 13, and it's changing at a pH between 12 and 14. So the stronger the acid is, the lower the pH is at which it changes, whereas the weaker the acid is, right, and this is the weakest one because it has the smallest Ka, the higher the pH is at which it's going to change. So not all weak acids have the ability to be indicators. There has to be a color change. If there's no color change, right, if you think about vinegar, right, vinegar is colorless and its conjugate of acetate is also colorless. So it's useless to me as an indicator because it doesn't change colors. So what we find is for something to be good as an indicator, there has to be a difference in colors between the conjugate pairs. So either one is like blue and the other one is yellow, or we find that there's one that's colorless and then the other one has a color associated with it, okay? So if we look at chlorophenol red, right, chlorophenol red, if we look at our data table, has the abbreviations of HCH and CH minus. So this has the ability to set up an equilibrium system, where this is going to be in equilibrium with its conjugates, which are going to be the CH minus and hydronium. Okay, so part of why when we add indicator we only want to add a couple of drops is we are technically adding an acid to our solution. And that does have the ability to change the pH somewhat. So we only want to add a little bit, okay? So how these work. This has one color. This has a different color. If I look in my data table and I find the chlorophenol red, we have HCH and we have CH minus. We're told the color changes yellow to red. So the HCH is one of those colors. So if we think about it, so I'm trying to find where I have this, we could recognize that in an acidic solution, right, that would mean that we would have increased the concentration of the hydronium. Sorry, my dog is currently rolling on the floor and being very special. She likes to be special, in case you hear grunting in the background. Okay, so in an acidic solution, we have increased the concentration of hydronium. So if we increase the concentration of hydronium, the system wants to decrease the concentration of hydronium, and it is going to result in a shift to the left. So because we only add this in small quantities, this isn't going to be a buffer. It's going to shift all the way over. So what we're going to find is that in acidic solutions, we are basically just going to have the HCH. We're not going to have any of the CH minus because it will have shifted all the way over. So when we look at the colors, right, we saw that for chlorophenol red, if 5.2 to 6.8, it changes from yellow to red. So in acidic solutions, it's going to be yellow. So from that, I can recognize that this here has to be my yellow species, the HCH. In basic solutions, we see that it's the other color, which was what? I didn't pay attention. Was it red? Red, yeah. So this guy here is going to have to be the red one, right? The other way we can figure that out is in basic solutions, we would have increased the hydroxide. Hydroxide is going to neutralize the hydronium and thereby decrease the hydronium. That's going to cause my system to shift to the right, and that's why I'm going to see the red color that appears in the solution, okay? So for the most part, what you find when you look at this data table here is when it gives you this and it gives you these colors, they already kind of go the way they match. So HMV is yellow and MV minus is blue. So if you think about when we use indicators, right, and bromothymol blue is kind of the most common one you're used to. You know you can get yellow, you can get blue, but you also know that you can get green because green is the color between yellow and blue. So the reason we get green is because we have approximately equal concentrations of this guy, which is yellow, and this guy, which is blue. So when we look at it, when we mix those two colors together, it does appear to be green. However, and some of you guys will see this, especially when you do those acid-base titrations, right? Sometimes you actually get blue, but sometimes you look at it and it's like you swirl it and it's like, well, this part's yellow and this part's blue. And then you swirl it some more. Now maybe it looks a little more green, but then it kind of separates back out into those two colors. But you can see both colors. And that's just because you do technically have both colors, and sometimes they just distribute weirdly in the solution, okay? So important to recognize that indicators are all going to be weak acids. pH at which they're going to change is going to be dependent on their strength. You should be able to use indicators to approximate pHs of unknown solutions. You did a lab like that in Chem 20. You're going to do a dry lab like that in Chem 30, right? If you remember last year, you kind of put all the little dots on the sheet of paper and you made all the colors of the rainbow. If you did it second semester, obviously you didn't get to do that, but if you did it first semester, you definitely did do that, okay? So let's look at some questions. So a tablet containing an unknown acid was dissolved to make 100 mL of solution. The entire solution was then titrated with 0.2 mole per liter sodium hydroxide. The data were collected and graphed as shown below. So here's our little graph. So for this titration, a suitable indicator and its corresponding color change are. So first thing I want to do is figure out where the equivalence point is, right? So here's my dip because I have a weak acid. Here's my vertical. So the middle of my vertical is probably going to be right around here, right? And obviously a question like this is open somewhat to interpretation, but I'm going to be looking for an indicator that changes around 7.5, 8, somewhere in that range, okay? So the other thing that's really important to look at, because it's asking about the corresponding color change, is to recognize, did I start with the acid in the flask or the base in the flask? In this case, I started with the acid in the flask, so my color change is going to match up with what I see in my data booklet. But if I started with the base in the flask, my color change would be the opposite from the order in which it appears, right? So, some options. Apparently I only put 3 options, so clearly missed option D. So there's phenolphthalein, indigo carmine, and thymol blue. So in this case, we're going to narrow it down just based off of that pH, right? So phenolphthalein is going to change at 8.2. That's pretty close to what we're looking at. Thymol blue could as well, because it's going to change between 8 and 9.6. And then what was my other option? Indigo carmine. That one's not going to work at all, because when you look at indigo carmine, that doesn't change until 11.4. So we know that indigo carmine is out. So we're left with, no, I just totally crossed the wrong one out. That indigo carmine is out. So either it's going to be thymol blue or phenolphthalein. It's just going to come down to the color change that we have happening. So phenolphthalein, colorless to pink. When we look here, phenolphthalein, we're starting with an acid, so it is going to be colors, is going to go to pink. So that one definitely works. If we look at thymol blue, we would be looking at the color change that corresponds to that pH close to 8, right? So that would be this one here, and that would be yellow to blue. So when we look at the thymol blue, it's giving us red to yellow. So that is not it. Our correct answer is going to be A, because that's actually the appropriate color change that we're going to see. Okay, so here's another one for you. So Kelly tested portions of a solution with 3 indicators to determine the approximate pH. So there's your indicators, the colors, the approximate pH of the solution is. So we're going to have to go through the 3 indicators and kind of narrow down our range. So we have that bromocresol green is blue. So we find bromocresol green. If it's blue, that means it's going to be greater than 5.4. So from here, we know greater than 5.4. Okay, indigo carmine is blue. So here we find indigo carmine blue means that it's going to be less than 11.4. So we know it's less than 11.4. So now we know that the pH is somewhere between 5.4 and 11.4. The question just becomes, can we narrow it down more using the last indicator? So thymolphthalein is blue. So thymolphthalein is here. If it is blue, which is on this side, that means it's a pH greater than 10.6. So we know it's greater than 10.6. It's pretty awesome writing on my little keypad. Okay, so from here we can narrow down that the pH has to be somewhere between 10.6 and 11.4. So the only option that is between that is going to be C. So we are going to choose C. Okay, so here's our next one. So 1.80 grams of CH3COH are dissolved in enough water to make 300 mils of solution. If the indicator dropped into the solution is blank, the color of the solution will be blank. Okay, so pause the video here, take like 5-10 minutes to try to solve this. Once most of you have this, you guys can resume watching the video. So hopefully where you went with this question, you would have had to do some stoich at the beginning to determine what was the concentration of the acetic acid, because it only gave you a mass and a volume. So from there we could figure out that the concentration is 0.0999. Okay, then what you need to do is you need to set up an ice table. You need an ice table because this is a weak acid. We create ice tables for those. Really common mistake you guys make with this question is you just do stoich and you're like, oh, it's a 1-to-1 ratio, and then you figure that out. But you can't do that because it is a weak acid. So we're going to set up our ice table. We have an initial concentration that we calculate as 0.0999. Do an approx check using the K. So that concentration divided by, what was it, 1.8 times 10 to the negative 5, I want to say. You can approximate because you got like 5,000 and something. So what that's going to mean, we can get rid of the minus X that's here in our ice table. We set up our equilibrium law expression. So Ka is the acetate times the hydronium divided by the acetic acid. So we get our 1.8 times 10 to the negative 5 equals X squared divided by 0.0999. From there, we can figure out what X is. And from X, we can figure out what that pH is, because it's going to be negative log of that concentration. We wind up with 2.873. So now we can go all the way back up to here. So we know that our pH is 2.873. And we can try to figure out what color that indicator is going to be. So we have orange 4. If we look at orange 4, it's going to change between 1.4 and 2.8. So 2.873 is on the greater end of that range, therefore it would be yellow. So no, it is not going to be orange 4, because it says orange and it wouldn't be orange, it would be yellow. Okay, bromothymol blue. The solution is going to be blue. If it's blue, that would be greater than 7.6. This is 2.873, so it is not. Okay, methyl violet is going to be yellow. So you find methyl violet, it's only going to be yellow when the pH is 0 or less. Then we get thymol blue, and it says it's going to be yellow. So thymol blue, when you look at it, is going to be yellow between a pH of 2.8 and 8.0. We're at 2.87, so we fall in that range. Therefore, it is going to be D. Okay, for those of you that just did stoich, I want to say you would have found A, right? And so that's why they kind of picked something that was right on the borderline. This is going to check to see, do you actually recognize that you couldn't do stoich for this question because it is a weak acid and you had to set up that ice table. Okay, here's another example. So 200 mils of 0.125 molar solution potassium hydroxide was added to 100 mils of 0.1 molar solution of nitric acid. Which indicator is coupled with the effect it would produce in the new solution? So this is going back to questions like we did, I want to say on like day 2 of this unit, where we looked at those weird titration calculations where they were really limiting and excess questions. So same deal as the last question, go ahead and pause this, and then once most of you are done, resume the video to see what you should have done. Okay, so we have our neutralization equation of potassium hydroxide with nitric acid to give us water, potassium nitrate. We were given the volume of potassium hydroxide as 0.2 and the concentration is 0.125. For the nitric acid, we are given 0.1 liters and 0.1 moles per liter. From those, we can calculate how many moles of potassium hydroxide we have just by multiplying these. And then we can figure how many moles of nitric acid we have by doing 0.1 times 0.1. So when we look at these, we can see that we have more potassium hydroxide. This is the bigger number, therefore it is the reagent that is present in excess. We need to figure out how much of it is going to be left over once we neutralize that 0.01 moles of the acid. So we do our 0.025 minus 0.01. We come up with 0.015 moles of KOH remains. Because it's KOH, it's an ionic compound, it's base, it's going to dissociate potassium ions and hydroxide ions. It's strong because it's a group 1 hydroxide, which is why it's a single-headed arrow. It means we get to do our stoich. So we have our ratio, our 0.015 moles of KOH, and then we need to divide by the volume. Remember, it has to be the total volume because we combined the 200 mils and the 100 mils together. So we're going to use the 0.3 liters. It gives us a concentration of hydroxide of 0.05. From that, I can calculate what my POH is because it's negative log of the concentration of hydroxide. So I come up with a POH of 1.30. From that, I can calculate the pH by doing 14 minus. So I come up with 12.699 when I use all the numbers that were in my calculator for that one. So now that we know that the pH is 12.699, we can actually go about answering this question. So orange 4, it says it's orange. So if we look at our data table, orange 4 being orange would be a pH between 1.4 and 2.8. We don't have that, so it's not A. Okay, thymol blue being orange, again, looking at your table, that would mean a pH between 1.2 and 2.8. So that is also out. So indigo carmine being green, that would be a pH between 11.4 and 13, which we do have. And then phenolphthalein being colorless, stops being colorless at 8.2, so that one is out. Okay, so we're left with only C as the correct answer. All right, so that concludes your indicators and also concludes your acid-base equilibrium. Definitely a little theory in this unit as well as some calculation pieces. So really important to make sure that you are practicing both as you start to get ready for your unit test.